So this topic corresponds to section 2.2 from the Corman's book. So let's start. Okay. So when we are going to discuss data structures and algorithms, we are going to analyze them. But instead of analyzing them on a particular physical computer, we are going to create an abstraction. We are going to create a model of the underlying computer. Okay. So before we go into the details of that particular model, we should understand one basic thing, which is all models are wrong, but some models are useful. This is a famous quote which is generally attributed to statistician Box. So let's take a few examples. I'm sure in your high school days or in your college days, you must have studied the projectile motion. Okay, and if you remember, when you modeled the projectile motion of an object, you made several assumptions. Okay, for example, if you are throwing a particular object, you assume that the object is a single point, which is not true. Then you assume that when you throw that object into the air, there is no air resistance. Okay. Then you assume that the only gravitational force that is acting on the object is the gravitational force of the earth. Well, which is again wrong, because every other physical body would exert gravitational force onto that particular projectile. Okay. Then you also assume that the gravitational force of the earth on the object is constant throughout its journey, which is again not true, because this force depends on the distance. Okay. So there were several approximations in this particular model of the projectile motion. Okay, but still you studied that particular model. Okay, why? Well, because even if there are many inaccuracies, the answer that it gives is good enough answer. Okay, so although it does not perfectly represent the real world, still it can give us the good enough idea of the real world. Okay, and that's why that particular model is useful. Similarly, you have studied the relational model in relational databases. Okay, so the way it models the data is that everything is stable. Okay, so no matter what data you want to represent, you always represent it as a table, and then you have a set of columns, and those columns represents the attribute, and that's the way you try to fit in any data. So if you are storing information about students, it becomes a table. If you are storing information about a network, it is stored as a table. If you are storing documents, it is a table. If you are storing images, videos, everything is still modeled as a relation, and it goes into a table. Okay, so is it right? Is it wrong? Well, it depends on how much approximation, how much inconvenience you can accept. Okay, so any model that you pick up, you will always find out its inaccuracies, but at the same time, the model can be useful, and if it is useful, we typically use that particular model. Okay, so let's look at the real world electronic digital computers that we have. So which are some of the important aspects that we see? Okay, first thing we notice that real world computers, they have a memory hierarchy, which means that you would have your secondary storage, which is typically a hard disk. Then you would have your primary memory, which is random access memory or RAM, and then you would have memory inside your processor. Okay, which would be in terms of the registers. Okay, but apart from that, there are many other layers to this memory hierarchy. Okay, for example, your processor would have multiple layers of cache: L1 cache, L2 cache, L3 cache, and so on. Okay, then the real world computers these days, they are multi-core. So no matter which computer you buy today, it would have multiple cores, which means that these cores, they can execute multiple instructions on their own, and you can have multiple programs running simultaneously. And then some of the computers are even multi-processor. So not just a single processor, you have multiple processors inside your computer. Okay, and then the instructions that are executed by these processors these instructions have varied level of complexity. So some of the instructions, they can be completed in single clock cycle, some might require 5 clock cycles, some might require 10 clock cycles, some might require number of instructions depending on various other factors, and so on. Okay, so there are many complex issues in the actual real world digital electronic computers that we have. However, when we build the model of these computers in our data structures and algorithm class, we are going to ignore these properties. Okay, so we are going to settle for something really simple, something which is easily tractable, analyzable. Okay, so we are going to assume that there is no memory hierarchy. So we'll say that we store our data in memory, but we do not bother to think whether that data is in secondary storage, or whether it is in the RAM, or is it in the processor cache, or is it in processor register. Okay, in real world this matters, but for our analysis we are going to assume that, well, data is just in memory. Okay, then we are going to assume that our computer has a single processor, single core. Okay, and it executes only a single instruction at a time. Okay, so we are not going to think about any pipeline or any other complexity that comes from the modern hardware. Okay, so it's a simple computer with single processor. It executes just a single instruction at a time, and then we are going to assume that all these instructions, they take exactly same amount of time. So no matter if you are doing addition, you are doing subtraction, multiplication, division, you are loading a value into a variable, so any instruction that you consider as part of your pseudocode, will assume that it takes the unit amount of time, it takes exact same amount of resources, it has exact same cost. And all these three assumptions, they are in contrast with the real world computers. But then the question comes, why use such a model? Okay, easy answer is that this model is convenient for analysis. It makes our job to analyze data structures, algorithms very easy, very convenient, but that should not be the right reason. Okay, so the right reason is that even though it is not perfect, this model is observed to be good enough. Okay, for example, if I take algorithm 1 and algorithm 2 for a particular problem and do the analysis of these algorithms using my simple random access machine model, and if I observe that algorithm 1 is far faster than algorithm 2 on this random access machine model, then in real world most of the time that's what is going to happen. Okay, so the gap between the running time that we observe in RAM model might not be the exact same gap that we observe in real world, because in real world all the other factors are going to come in picture. Your memory hierarchy, your multi-core multiprocessor architecture, and the variety of instructions. Okay, these factors are going to play their effect, but generally they won't be that significant so that they would change the answer about which of them is faster. Okay, it would just change the difference in their speed, but still the one which is faster on our RAM model would still remain faster in the real world model. Okay, so now we are going to henceforth deal with a simple abstract computer which has these attributes. Okay, no memory hierarchy, single processor, single instruction at a time, and all instructions are of the same value. Okay, so with this as the model of our computation, we'll proceed further with this course.